Hi everyone. In this video, we are covering our very last chapter of content in this course, which is about regression and correlation. Regression and correlation describes the relationships between two interval ratio level variables. And so this goes back all the way to our very first chapter that we covered, where we described the various levels of measurement. So whether that was nominal, ordinal, or interval ratio. And so for correlation and regression, this is where we are dealing with the concept of associations between two or more interval ratio level variables. So we are once again returning to the idea of independent variables, which as a reminder are the cause variable, and a dependent variable, or think of that as the effect. And with regression in particular, we are focusing on a linear relationship between two variables, or think of that as a straight line. And one way that we can quickly and easily visualize the relationship between two interval ratio level variables is to plot this out on a scatter plot. And so if you recall all the way back from Unit 1, we talked about the different ways that you could display or show or graph different types of variables, whether that was on a histogram or a bar chart or a scattergram similar to this. In this case, when we use interval ratio variables in particular, we can easily see the relationship between two variables if we just plot them out here. And so, for example, if we put our independent variable on the x-axis here, which remember is always on our bottom, and our y-axis, which is our dependent variable here on the top, we can start to see a relationship start forming here. In this case, it looks like a more positive relationship. So as our x-axis variable is increasing here, so is our y variable increase. Let's take a look at an actual example here on the next slide of how this might look in a real-world example. In this example, we are going to assess height and the relationship that that has to shoe size for men in the United States. But before we get started with actually charting out this scatter plot, let's ensure that we actually have two interval ratio level variables here before we even get started, because that's the requirement we have to create a scatter plot in the very first place. And so with height, we are going to measure this in inches. And knowing that that is my scale, I know that this is an interval ratio level variable because it is a numeric value and it has measurable points in between it, and I could calculate the difference between that. In other words, I know that someone who is 65 inches tall is 5 inches taller than someone who is 60 inches tall. Same goes for shoe size. We are actually going to measure this on a scale of 0 to 15. And so I know the increments between those are numeric in value. And I know, for example, that someone who is a size 12 is 3 sizes larger than someone who has a size 9 foot. And so let's take a look here. We also know what we're going to be using for our x and y variable. Again, our x or independent variable will always go on our horizontal axis. So that's what we'll be doing here. And on our y-axis will always be our dependent variable. So that will be shoe size in this case. So now what I would like you to do is kind of think through the relationship that you think these two variables might have to each other. What would we expect? Would we expect shoe size to increase while height increases? Or would we expect there to be a negative relationship? So in that case, would shoe size increase while height decreased? Or would we expect a spurious relationship, meaning that it's kind of all over the place? We're not expecting any pattern here at all. It could be all over the place. So think through that before I show you what an actual scatter plot of this information could look like. If you need to pause the video, go ahead and do that here. Okay. Here's what an actual scatter plot does look like. In this case, we are going to take a look at, after I do some erasing here, what the actual scatter plot looks like for this chart. And in this case, we can see that there is a positive relationship between our two variables, meaning that as an individual's height increases in inches, which we can see right here, so does their average shoe size. Again, this isn't perfect, right? It isn't in a straight line. So we know that sometimes people could have a higher height in inches and a little bit of a smaller shoe size than we might expect, or vice versa, but the general trend line or association is trending positive, meaning, again, as an individual's height increases, so in general does their shoe size. So that's what we can do quickly with scatter plots, is see general associations between two interval ratio level variables and see if there's just any general relationship between those two. Now that you've seen a real-world example of a scatter plot, let's take a look at the three key things that you should consider when assessing associations, correlations, or scatter plots in general. The first is whether or not a relationship exists between the two variables of interest. Or in other words, does the distribution of y, the dependent variable, change for the various conditions of x, or the independent variable? So thinking back to the scatter plot that we just covered, the distribution of y, or the dependent variable, was shoe size. So I'm going to designate that quick here with an SS. And the independent variable was height. And so what this is simply meaning here in terms of whether or not a relationship existed is basically, did these two variables have any association? Was there any general trend that we saw once we plotted them out? And the general trend that we saw was that as the independent variable increased, or in this case, an individual's height, so did their shoe size. And so in this case, the independent variable was exerting an effect on the dependent variable. So yes, it was changing for the various conditions of y, or in other words, as x increased, so the independent variable is changing that condition on y, so is the shoe size increasing at the same time, in general, right? It's not a perfect straight line, but the general association and correlation was as one was increasing, so was the other. The second component you want to consider is how strong is the relationship between those two variables? This is essentially the question that we will be grappling with for the remainder of this presentation, and so we'll revisit this much later in this presentation, pretty much for the rest of the time. So I'm going to table this one for now, and we'll come back to it. And the third one is, what is the direction of the relationship? Is it positive or negative? And so what you can ask yourself here is, what is happening to these two variables at the same time? An indicator of a positive relationship is if both variables are increasing at the same time. And this is what we saw in the scatter plot just before, right? As an individual's height increased, so did their shoe size, right? Both were increasing at the same time. So a general positive relationship looks like this. A negative relationship is the exact opposite, as you can imagine. And this occurs when one variable is increasing while the other variable is decreasing. And so this is the general trend line that you would see for a negative relationship. And so these are the three factors that you should really think about when you're assessing a scatter plot, a correlation, or any type of association between two interval ratio level variables. And there's a specific type of correlation coefficient that we will be assessing as well that will help us actually measure this relationship, and we'll get to that on the very next slide. And the name of that correlation coefficient is Pearson's R. Now, Pearson's R allows us to measure the association between two interval ratio level variables. Or in other words, we can actually quantify both the strength and the direction of the relationship of our two variables of interest. And so Pearson's R is actually measured on a scale of -1 to +1, in which our middle point is actually going to be 0. And so thinking back all the way to unit number 1, this is going to be a range of values from this scale listed here. So let's take a look at these graphs on the side to see where the extremes of both ends of our range are. Starting off with our perfect negative correlation. And so this is an example of a -1, or in other words, a perfect negative relationship. So in the real world, this is extremely rare to actually happen, and I can't even think of an instance in which it could happen in reality, because that means that for every single unit in which one variable increases, the exact same unit has to increase at the same time. So again, With a negative correlation, that means that one variable is increasing and the other is decreasing in the exact same increment if you were to have a perfect relationship, which is what you're seeing here. So that is what we're seeing in terms of that. However, you could also see, because this is a range, a variable that might have a negative 0.75 relationship. So it's not going to be perfect necessarily. It might look something like that, a little bit more of a straighter line there. That would still show that one variable is increasing while the other is decreasing. It just might not have that perfect line that you see here. Same goes for our perfect positive correlation. So again, this looks similar to what we saw in our scatter plot for both height in inches and shoe size. However, what we're seeing here is a positive 1 for our positive relationship. So we're now on the extreme end of our range here. So in this case, we see that for every unit increase on our x-axis, we also see that increase occur on our y-axis as well, and they happen in the same increments. And so again, this doesn't often happen perfectly in real-world examples. Again, I don't think I could think of one. Even thinking back to our scatter plot, we didn't see that every single person that happens to be 6 foot has the exact same shoe size, right? There's some variation among that. We can't perfectly predict that every single person that happens to be that height is going to have the exact same shoe size. So it's not always going to be this perfect correlation. We're going to see some general trend line around here, and we're going to have different actual values all over the place here. And so we're not expected to see either of these in the real world, right? But we're talking about general associations and correlations, and that's what Pearson's R allows us to measure. And so the strength of that relationship is measured as we get a higher number in either direction. So the closer we get to a value of either -1 or +1, the higher the strength of that relationship is, right? Because we're getting closer to perfection, either in a negative direction or a positive direction. The very last graph you're seeing here is 0, which is that middle range here, right? That's our center point of this relationship between these two. What you're seeing here is called a spurious correlation, meaning there isn't one, right? There's no correlation that we can see between these two variables. If I tried to draw a trend line or any association between those two, this doesn't work, that doesn't work. I can't get anything that shows me an actual association between these variables. And so because of that, there is no strength or association to this relationship. I don't know if it's going in a positive direction or a negative direction, or what that strength actually is. And so because of that, it gets assigned a value of 0. And so the further you get in either direction increases the strength. And then in terms of the direction, that will be assessed whether you have a negative sign here or a positive sign. So those are the two questions to ask yourself here. Again, strength is determined by the closer the value you get to either a -1 or a +1. And then that direction is determined by the sign you receive, right? Is it negative, indicating a negative correlation? Or are you having a positive Pearson's R score, indicating a positive correlation? So let's talk a little bit more about Pearson's R and that correlation coefficient altogether. Here's what it looks like plotted out in terms of our actual X and Y axes and our 0 relationship or our spurious correlation here at the bottom. Again, there isn't any relationship between these two. If it helps you to visualize it this way rather than the previous graphical representation, please keep this one in mind too. I find it a little bit easier now that our graphs are all labeled correctly. And you can keep in mind that our independent variable will always be on our x-axis here, and our dependent will always be on our y. And so this is a good one to come back and reference if you ever have a real-world example and you want to double check, which one's the independent, which one's the dependent. And if I see that I might have a positive or a negative relationship and you just want to check what direction that's going in, this is a good reference slide to come back and take a look at. So you might be asking yourself now, I know what a Pearson's R is, right? It's going to tell me the strength and the direction of a correlation or an association, but how do I actually calculate that? Well, here's how you actually do that. And I know this looks like a nightmare of a problem and a calculation here, and that's because it is. The actual calculation and base formula for this is quite extensive. What you would do, and I'll break this down for you here, is you would add up the difference between each x and the mean. And so if you think of this in terms of our scatter plot here, what we're essentially doing is if we had a trend line, we are looking and calculating the difference between each of these dots here relative to what the true average or trend line is here. And then we're multiplying that between the difference between each y and the mean. So we're doing this for both sides of the equation here. And then what we're doing is dividing that by the square root of summing together all of those points as well, but squared, and then doing the same thing and multiplying that by the sum of all of the differences between the y values or the dependent variables squared as well. So we're really trying to determine what this average line is, right? Is it going to be positive or negative, and what is that strength? Again, I know this looks really overwhelming, which you'll be happy to find out is exactly why I am not going to have you calculate it yourself. The overall purpose I want you to have for the purpose of this class is to simply recognize what Pearson's R is. Again, those two questions we just covered in the last slide. Again, assessing the strength and the direction of a relationship. And really what this is for is if you want to continue in a higher level statistics course, whether that's multivariate regression or anything beyond that step as well, this is where you would get more into the formulaic responses and actually calculating this by hand or having a higher level statistical software do this for you. And so for our purposes, again, those are the two questions that I just want you to recognize here again, strength and the direction of the relationship. And so with that in mind, let's go back to our very first scatter plot example. And so, revisiting our very first scatter plot of height and shoe size, what we can do now beyond just saying what the relationship we generally saw there is actually assessing Pearson's R. And so, I've run this calculation for you, meaning I've actually calculated this. I haven't by hand. I had a statistical software program do this for you. It's actually very easy and a very basic thing to have either SPSS, Stata, or R. Again, these are higher level statistical software programs if you are interested in them. Again, perhaps you could take a higher level statistics course if you're interested in this. Again, chapter 12 is kind of your introduction to a next step of statistics if you're interested in that. But again, this is something that it can quickly calculate for you. So Pearson's R. Let's assess the two questions that I want you to know based on this result here. Again, the strength of the relationship and the direction of that relationship. And so let's keep those two questions in mind. So the first thing here, let's talk about the direction, because I think that's always the first one, and you got a 50-50 shot in what direction, is it positive or negative, to figure it out. And the key indicator here to figure out the direction is to simply look at the sign. Is our Pearson's R value positive or negative? And in this case, I see that we have a positive number here. It is positive 0.866. So I know that our direction is positive, which is great. We also knew this from simply looking at this chart as well. And so I mentioned on a previous couple of slides that if you ever needed to go back and reference what a positive scatter plot looked like versus a negative scatter plot, that's a good reference page for you to have in mind if you want to see what those look like in general. Another way we can double check this is by actually taking a look at our X and Y axes. So, knowing that our independent variable here is height and our dependent variable here is y, we can see that as our height increases for men, so does their shoe size, right? We are seeing that both increase at the same time, indicating an overall positive relationship. And so we are good to go on that. So multiple ways that you can check on this here. I think the obvious is simply to look at your r-squared value. Is it a positive number or a negative number? But if you want to double check yourself as well, there's multiple different avenues that you can do that as well. So now that we took a look at the direction, let's now assess the strength. And so as I mentioned, Pearson's R is measured on a range scale of -1 to +1, in which our middle point is 0. So let me plot that out here a little bit. Got our 0 point here in the middle, and then +1 on this end. In terms of our strength, what you can kind of think of on both ends is we want to see how strong it is in terms of perfection on either side. So +1 represented a perfect positive relationship, meaning that it would be an exact 1 unit increase for each independent and dependent variable as it went at the same time. So in other words, for this example, again, as we increased a certain amount of height, so would the shoe size, and that would be in every single increment. So it could be in this example, for every 2 inches gained, so does the shoe size, right? It depends on what our actual findings would be here, and it's not clearly in this case because we see that our Pearson's R is not a perfect +1, but in general, that's how we would think about this here. Whereas a -1, in terms of strength, we would see a perfect negative relationship, which is where one variable is increasing while the other is decreasing. But for our purposes here, we already figured out that this will be a positive direction, so let's take a look at our strength on this side. We know that 0 indicates a spurious relationship, or in other words, there is no or 0 correlation between the two variables. And if you needed to go back and take a look at what that looks like, basically, it's just a scatter plot with a bunch of dots all over the place, right? There's no clear relationship between the two, and you can't draw a trend line between them. There's no indication of whether it would be positive or negative, or what a strength would be in between them. And so what you want to ask yourself at this point is, where do I fall in terms of our range between 0 and +1? In this case, with a value of 0.866, we're definitely closer to our +1 here than we are to 0. Even visually, by taking a look at our trend line here, we are seeing a pretty strong positive relationship here. In terms of this, how I would describe this is that we are seeing a relatively strong relationship between our independent variable of height in relationship to our dependent variable of shoe size. If this R happened to be within the range of anywhere between, let's say, 0.5 and 0.7, I would probably say that that is a moderately strong relationship. It would be a little less steep here in terms of that overall trend line. We'll get to a couple other examples of this in a minute, but this is one of the more stronger strengths that we could have in a real world scenario like this for sure. Again, perfection on either side of these scales is going to be extremely rare in actual circumstances. And so our strength is very high in this point, and I would again actually articulate this as a very strong correlation between these two variables. So our strength is high. So a couple of different ways you can go about that. It's strong, or our strength is high as well. Let's take a look at another example of how we could assess Pearson's R in another case scenario. Another one we could take a look at is the number of hours an individual spends studying and their subsequent GPA. And so our x-axis here, or our independent variable, is going to be the number of hours studied, and that is measured in hours again. We can see that here from the top, in relationship to their overall GPA, which is our dependent variable, measured on a scale here of 0 to 4, but we see that no one scored below a 2, and so it's just cut off here a little bit for our sake. But again, measured on that 0 to 4 scale, we see a couple people reached a 4.0 here. And here I've already calculated for you Pearson's R as well. And so we're going to again assess two questions here. that we are going to be taking a look at, again, same two that we did for the previous example, that is going to be the direction of this relationship and the strength of that relationship. The first thing that we can take a look at is the direction. And again, the first thing that I ask myself is whether or not my Pearson's R value is positive or negative. And in this case, right off the bat, I see that I once again have a positive R value for my Pearson's R. And so I know right off the bat that my direction is positive. It doesn't look just like the example we saw in the previous slide, but I know that it somewhat mirrors it, and I didn't have a negative relationship here either. So I don't see a negative number. It isn't quite the trend line that we saw in the last one, but that's also indicative of the strength here, which is what we'll talk about right now. Again, thinking back to how Pearson's R is measured. Again, we're taking a look at a scale here of -1 with a middle point of 0, ranging all the way to our perfect positive end here of +1. Knowing that I fell on the positive side here, meaning that as an individual increased in their number of hours studied, so did their GPA. And this makes sense to us in reality, right? We would expect that someone who spends more time studying has a higher GPA. If it was the opposite and it was a negative relationship, and the fewer hours you studied, the higher GPA you had, that would kind of turn our entire school system on its head, right? So this is a good thing for us to actually find out that, in other words, studying is effective. It's an effective study tool to allow you to do better at school overall and on your exams. In this case, though, I see that my Pearson's R value is not quite as high as I saw in terms of the correlation and association value for our previous scatter plot example of height and shoe size. Reason being is now my Pearson's R value is only 0.5. So what does that mean for us? Let's take a look at the trend line here. We can see that it's not quite as steep as we saw in the previous relationship. Again, what I kind of noted here is what we saw with the relationship between height and shoe size. So we can kind of think through this logically of what this would look like in a real world case scenario. When I was thinking through this example, I thought back to my experiences in both high school and undergrad. And there were some people who didn't need to study at all to do well on exams and their homework. And so those are people who are up here in this category, right? They only studied about 4 to 5 hours and they have a perfect 4.0 GPA. On the very opposite side, though, I see that someone studied and reported nearly 50 hours of studying per week, and they also have a perfect 4.0 GPA. So they're fulfilling what we would expect in terms of the overall positive relationship, but we're also seeing some outliers here as well, right? On the flip side, we also see that some people who studied really, really hard, almost nearly 50 hours, only had about a little over a 3.5 GPA, where some people were able to achieve that by only studying for about 8 hours here, maybe about 17 hours here. And so it's not a perfect relationship. Overall, what our trend line is showing us is that in general, the more you study, the higher the GPA you're going to have. But we do have some exceptions to this rule, clearly, right? We have our smarty pants over here who, they don't have to study at all. They just walk into the classroom and somehow they're able to do well on everything. And then we have people who, I would consider myself in this category, who had to try really hard at school to do well, right? I was studying all the time. I had to do and put in a lot of extra time and work. And sometimes it paid off and sometimes it didn't. And so I would definitely fall into this category over here. And I'd be really frustrated with the folks that were able to just walk in and do really well. One of my best friends is like this. So she would definitely find herself up in this category. And so the strength of this relationship, I would categorize as a moderately positive relationship. I kind of mentioned that on the last slide as well. So I would say this is moderately positive. we can still see that the overall trend line here is that as the number of hours increases, so as we're moving along our x-axis in a positive direction, as that increases, so does our GPA, but it's not nearly as strong as we saw with the relationship on our previous scatter plot. And so this shows that there still is a relationship overall, but it's not perfectly predicting what we would expect in terms of an hour number studied, in terms of an overall GPA. We couldn't say for certain that if you study 50 hours per week, you will have a perfect 4.0 GPA. If we did receive a Pearson's R of exactly +1 here, then maybe we could make that claim, and then essentially we'd figure out the entire school system, right? Because all we would have to tell students is if you study X amount of hours a week, in this case 50, you'll ace school, right? You'll get a perfect 4.0 GPA. And if you don't, here's where you'll end up if you study 0 hours, 10 hours, 20 hours, 30 hours. But again, it's not perfect. So overall, how I would report this, if I were to give context to this problem, is that in general, the more that you study, the higher your GPA will be. It is a moderately positive relationship, but overall there are some exceptions to this rule, meaning that there are some individuals who do not study as long as some of their peers and still achieve a high GPA, and there are some individuals who study well beyond the average of their peers and do not achieve a perfect 4.0 GPA. And that has to do with a moderately strong relationship here. All right, let's take a look at one more example that is going to actually show us the opposite type of relationship. This example assesses the relationship between the number of hours spent studying per week in relation to the number of hours spent watching TV per week. Our x-axis, or our independent variable, is the number of hours spent studying per week, and our y-axis is going to be the number of hours spent watching TV per week, or our dependent variable. You may have noticed by simply looking at this scatter plot that it looks quite different from our previous two examples. One of the indicators of that could be by taking a look at our Pearson's R value here. In terms of our direction, which is our first question that we want to answer here, I see that my sign here has flipped. Now I have a negative value for my Pearson's R correlation coefficient, whereas my previous two examples had a positive Pearson's R. Because of that, my trend line has switched in direction. As a brief reminder, a positive relationship or trend line is going to look like this, meaning that when one variable increases, so does the other variable. When I have a negative relationship, that means that when one variable is increasing, the other is decreasing, which is what we see here. Again, this is an example of more of a perfect relationship, which again doesn't happen in actuality all that often, but we'll get to that in just a second once we discuss the strength. Again, by simply looking at my Pearson's R, I know that the direction is negative, but we could also take a look at the scatter plot itself or by referencing the direction of the two variables in relationship to one another. But let's take a look at the strength because it is quite different from the previous two examples. Again, a Pearson's R is assessed on a range from -1 with a center point of 0 all the way to a +1, which would be a perfect positive correlation. In this case, we don't care about this end of the distribution at all because we only care about the negative end of the distribution, or the relationship between 0 and -1. As I had mentioned here on the left-hand side, if we had a perfect negative relationship, we would see a graph that looked similar to this, meaning that as a 1 unit increase happened for one variable, a 1 unit decrease would happen for the other variable. But that's not what we see here, right? R does not equal exactly -1. It equals -0.139. So if we had a scale here, imagine -1 all the way to 0, where do we fall closer to in terms of this range? We're definitely falling closer to 0 than to -1. this is where I will plot out our negative 0.139 here. And so what that's telling me is I'm closer to no relationship at all than to a perfect negative relationship. Remember that the spurious or no correlation line is a flat line like this. Again, go back a couple of slides to see that 0 point for a no correlation, right? You can't even draw a line, and so what a lot of times textbooks will do is just signify it by a straight line here. Whereas a perfect positive will be a perfect 45-degree angle like this, and same here, but just in a flip direction for our perfect negative. A straight horizontal line signifies our 0 correlation. So we don't quite have that here with our trend line. We still see that it is trending a little bit in the negative direction, but we're kind of trending here towards more of a horizontal line. We're kind of teetering on the balance here. And so overall, we could still say that there is a negative relationship. We know this by seeing that the direction of our Pearson's R is still negative, but the strength of this relationship is not really strong, right? This is a very slight relationship between those. So I would not say that the strength is very high in this case at all. And so what this means for us is that the effect that the number of hours spent studying per week does not exhibit a strong effect on the overall numbers of hours spent watching TV per week. So it's not saying that it's a perfect combination in this case, where you could assume that if you're watching a lot of TV, that you're also spending a lot of time studying, right? You only have so many hours in the week. So it wouldn't make sense that we could have people who are spending a lot of time watching TV also spending a lot of time studying, right? That's where we would form our perfect negative relationship. That can't happen in actuality, right? That would mean we would have a lot of people who are all over the place. But again, people have other activities that they have to do outside of just studying and watching TV. They have to eat, they have to clean, they have to go grocery shopping, anything else, right? We have other activities we have to account for. And so why it might make sense that we might see a little bit of a correlation here, the strength is not strong. This is a slight relationship, but again, I would say this is a not strong relationship. It is very slight at best, if I were to describe it that way. And so again, answering the two questions here, both a negative and not strong, we are certainly closer to there being no relationship than a perfect negative relationship. Again, if you're more of a visual person, think of it in terms of these three scatter plot images here. Go back to that reference slide a few slides ago about the perfect positive, perfect negative, and 0 correlation. Again, here, we're looking more like a horizontal line, but we still see the slight negative curve here. And so overall, our Pearson's R, our slight tilt here towards the negative direction tells us that we have a negative direction here. But because of the actual value here we see for our Pearson's R, we know that it isn't a strong relationship overall. The biggest takeaway I want you to have from this chapter, and possibly this entire class, comes from this slide here. So if I'm regaining your attention for the first time in a little while, this is the one to pay attention to. So far in this video, we have covered correlations, associations, and relationships, and how we can measure that quantitatively through Pearson's R, and how we can do that in terms of the strength and direction of those correlations. But the one thing that we cannot do is say that correlation equals causation. So let's think back to our first original scatter plot. The strength and direction of the relationship between height and shoe size was both strong and positive. However, we cannot say that an individual's height caused their shoe size to occur. In other words, just because someone happened to be 6 foot 2 inches tall does not automatically mean that they happen to have a shoe size of 12, right? It's not a perfect relationship. There is some variation among both height and shoe size. And so your big takeaway here is that correlation does not equal causation. So just because there happens to be a relationship between two variables does not mean that one is causing the other to occur. Now let's dive into the second half of our lecture material today, which transitions a little bit more away from the idea of associations and correlations and more towards the idea of regression. As I had mentioned previously, regression, and specifically multivariate regression, would be the next step if you were to ever pursue a higher level statistical course. So don't freak out too much about this. This is a very rudimentary introduction to this concept, and I won't have you do much calculation at all with this. But again, if you're interested in this any further, I'd be happy to talk to you about it more. So a regression line is what we call a line that is best fit for the data. And so what you see here on the right-hand side is if we were to truly draw our line of best fit, it would look something like this. It would connect all of our data points together, but we know that this wouldn't make sense to us if we were to provide this to another individual in terms of a direction, right? If we were to tell them, to take away any sort of pattern, correlation, or association between these two variables of number of hours studied and GPA, what relationship are they supposed to derive from this? It doesn't make a lot of sense, right? We could say any of these here, but given this data, it's kind of all over the place and it doesn't make a lot of sense to us. And so how do we figure out the best fitting line? Well, regression allows us to actually do that. In doing so, the regression line minimizes the variation of the scores, and it does this by taking the deviations of those differences between our actual observed Ys and our predicted Ys. So I kind of mentioned this before. What it's doing is it's taking all of these relative to the averages, and it's taking those differences and calculating them for us. It is then taking that variation as captured by our deviations and squaring those into an ordinary least squares, or what's known as an OLS model. Again, if you're not planning on taking any further steps into the statistical world, you will not need to know this moving forward. But if you are, OLS models are a very common way to enter the regression world. And so essentially what regression is having our line made up of all of our predicted Y values. And so a very simple way to kind of think this through is that any deviation, and this is going back all the way to when we talked about standard deviations, is that a deviation is simply the difference between a point and the line. So we're having our individual point to the predicted Y value, which you can think more of as the average, right? Because it's trying to fit all of these values into it. So it's our best fit model. Let's take a look at what the regression line calculation actually looks like. And in its current form, it is pretty simple. What we're looking at here is first our Y hat, which represents our dependent variable. So obviously this is going to depend on the context of the problem. And so I won't go any further than that for the concept of this base formula. What you see here is our alpha. This is our y-intercept, or in other words, where the line crosses the y-axis. So if we have our line of best fit, your alpha value is going to be that point here. Again, that's going to vary depending on the context of the problem. So if I had a line like that, it would be this point here. But again, that value will change depending on that, but it will be that point it crosses your y-axis. B is going to be your slope of the line, or how much your y-hat changes for every 1 unit increase in x. And so we'll get to on the next slide how you can actually calculate your slope. And lastly is your independent variable, which we always represent by x. So that's always what is on your horizontal axis as well. And so pretty simple in this format. However, once we get to actually estimating the regression line, it gets a little bit more complicated when we take a look at how we actually have to calculate our slope, or B. In order to do that, if we were to do it by hand, we would have to add up all of the differences between each x and the mean squared, multiply that by the difference between each y and the mean. And once we did that in our denominator, we would then have to add the difference between each x and the mean squared. and then divide that all together as well. And that's just the one component of that regression line. And then what we would have to do is then calculate our alpha, or the y-intercept here. What we would have to do to calculate that is take the mean of y and subtract that by our slope and our mean of x. And so our average of that as well. But as I've mentioned before, luckily, modern day statistical software has allowed us to not have us do this by hand. And I'm very grateful for that as well, because it's very tedious to go ahead and calculate this for each individual data point, right? This isn't even that large of a sample. So you can imagine if we had 500 people fill this out, you'd have to do that calculation for every single person here. This sample is much, much smaller than this, and it would still probably take you well over an hour to complete this problem. Luckily for me, what I did is just enter this data into a statistical software program called Stata, and it actually produced this regression equation for me. But let's walk through what this actually looks like. First, our alpha value here is telling us our y-intercept value. So that is our predicted value of our GPA when an individual studies for no time, 0 hours. And so what we could tell people, or as I had mentioned before, my friends who, they can walk into a room without studying and do very well on exams, is if you don't study at all, you could still have a predicted value of a GPA of 3.03 overall, which is solid, right? That's pretty much a B average. However, we're also trying to study the effect of number of hours studied on overall GPA, and we know that it's a positive effect. So what we're essentially trying to do is encourage people to study, right? We want people to do better overall at school and have a higher GPA. And so if we can show them incrementally, if you study more and more, what will happen to your GPA, that could possibly encourage them to study more. Again, this isn't a perfect equation, and as we discussed before, correlation does not equal causation, meaning that just because you happen to study more, your GPA will automatically increase. Overall, though, we know our line of best fit, which is our regression line here, tells us that theoretically, our best estimation tells us that it should increase given our trend line here. But again, if you study for 0 hours, you are predicted to have a GPA of 3.03. Our slope here is 0.02. So what does that mean within the context of this problem? So when study, or our X, is increased by a value of 1 hour, so basically when we increase every hour here, so 10 to 11, 11 to 12, 11 to 13, or 12 to 13, so on and so forth, your predicted GPA increases by 0.02 points. And so for those individuals that study 0 hours per week, they're basically accepting that they could have a predicted GPA of 3.03, right? We know, though, that some people barely study and they're still achieving a 4.0. But for some folks, that's not happening. And so if we want to encourage them to study more, we could show that, if you study more, perhaps you'll get a higher GPA, because our trend line is positively showing us this as well. So what this is telling us, though, is that using this information of this slope and our y-intercept here, we can now predict, based on the number of hours you study, what your expected GPA is going to be. So let's take a look at what this formula looks like written out. If this is easier for you to see it this way, I highly encourage you to use this format moving forward with any example problem. I visually like it to see it this way because all I have to do from here on out is plug in the numbers to get my estimated value for my dependent variable. That is what I will be solving for. In other words, we want to know the effect that the number of hours spent studying is going to have on overall GPA. Again, this regression equation was calculated for me. I didn't even do the work here. So these numbers will always be given to you. You will not be expected to do that by hand at all. What I want you to take away from this, though, is that by using regression, it allows us to actually predict things like this. And so we'll take a look at an example here of how we can actually use the regression line to predict overall GPA relative to the number of hours spent studying. So, using our equation, we can now predict GPA scores given the number of hours studied. So this was the equation that I had listed on the previous slide. So again, our y-intercept here was 3.03, which indicated to us that if you didn't study at all, so 0 hours, you would still be predicted to get a 3.03 GPA. But for every hour you study, you are predicted to have a 0.02 increase in your GPA. So now knowing that, with this regression equation, we can now calculate the predicted GPA value for individuals who study a certain amount of hours per week. So if you study 7 hours per week, you would have a predicted GPA value of 3.17. So the only calculation you really have to do here is plug in the value of 7, which is where you have your x here, which is our study value. So all you have to do is take 0.02, multiply that by 7, and add that to our y-intercept value of 3.03, and that's where you get this total here. Let's say you study 23 hours per week. Then your predicted GPA is going to be 3.03 plus 0.02 multiplied by 23. Then your GPA is expected and predicted to go all the way up to 3.49. Again, thinking back though to what I originally had indicated, if you study for no time, you're just going to have the value of the y-intercept itself. And so remember that if you multiply anything by a value of 0, it's just going to be 0. So the GPA is just going to be whatever value you have there. So again, what regression really allows us to do here is be able to predict these types of equations using our line of best fit. And so if you wanted to go all the way up to 50, right, the maximum really number of reported hours we saw in terms of studying, you could see what your predicted GPA would be. But again, if you look back at the scatter plot, that didn't necessarily mean that that individual had a perfect 4.0 GPA. In other words, correlation does not equal causation. We can get a general trend line, and it shows that as you increase your number of hours spent studying, your GPA should increase, right? We have that general positive correlation, but that isn't necessarily going to be a perfect case scenario for all individuals. So now let's combine the knowledge we have gained from both our variation discussion using Pearson's R and the regression line discussion that we just had. Remember that R is the correlation coefficient that tells us both the strength and the direction of the relationship itself. If we square this, we actually get a coefficient of the determination known as R squared. R squared actually can tell us the amount of variation in Y that is explained by X. So this is a very common statistical tool that even statisticians at the various highest levels will use to assess the amount of variation that is accounted for or not accounted for in their samples. And because of that, R square ranges from values from 0 to 1, where 0 equals no variation explained at all, and 1 equals all the variation explained. And so if you're a statistician, again, thinking about taking another higher level stats class than this, you theoretically want to see a higher R squared value in a multivariate regression setting. Reason being is you want your predictor values to be able to predict your dependent variable more so, right? You want to be able to account for more of the variation using the factors that you predicted would have that effect on your dependent variable. So you want to be closer to this value here. R square isn't necessarily perfect, especially in our social science world. It's very difficult to capture some of the variables we need to be able to actually account for some of the variation. Sometimes it's not even possible for us to do it, especially in a criminological sense, where sometimes it's unethical to calculate and collect certain types of data, and sometimes we can't even reach certain populations either. And so sometimes it's difficult for us to even reach certain types of independent variables and predictors that could account for some of the information that is explaining some of the variation in our R-squared value. If you were to get an ultimate R-squared value, and again, this is very easily calculated through a more sophisticated statistical software. Let's say you got an ultimate value, again, somewhere between this range of 0 to 1. It's really easy to actually interpret that within the context of the problem and just in general. If you received a score of, let's say, 0.42, that is a proportion value, as we learned all the way back in Unit 1. You could then say and quickly calculate that as a percentage that 42% of the variation in your dependent variable is explained by your independent variable, or if you were to do this in a multivariate setting, that you were doing this in terms of multiple predictors. So thinking back to our first scatter plot example, not only can we assess both Pearson's R, which tells us the strength and direction of the relationship and association, now we can take a look at R-squared and evaluate the amount of variation that these two variables are accounting for on one another. And so all you have to do is take Pearson's R, which was a value of 0.866, and square it, or in other words, just take 0.866 and multiply it by itself. We get a value of 0.75. And if we convert that into a percentage, we can say that 75% of the variation in shoe size is explained by height. And so you'll always say the dependent variable first, followed by the independent variable. Similarly, our second scatter plot example dealt with the number of hours studied and the number of TV hours watched per week. Our R value here for Pearson's was 0.5, so it was a moderately strong relationship, but still in the positive direction. In terms of R squared, again, all I took was that value of 0.5 and multiplied it by itself to get 0.25. What this tells me then is that 25% of the variation in hours of TV watched is explained by the number of hours studied. So again, I'm always addressing my dependent variable first, followed by my independent variable second. And so for a little bit of a table breakdown here, here's the difference between regression, R, and R squared. So if you need this as a reference, this is a good slide to take a look at. But as an overall reminder, for correlation, what we're essentially doing is assessing the relationship between two variables. Is there a relationship or a direction at all? If X and Y are related to each other in any certain way, and if the correlation coefficient R measures the strength and direction of that relationship, and again, thinking back to Pearson's R, that has a range of values from -1 with a middle point of 0 all the way to that perfect positive relationship with a value association of +1. Regression kind of ramps it up a little bit here. We now have a movement towards causal models with a direction. Again, we're not saying that correlation equals causation. Again, that's over here, and we do not want to conflate those two. But our slope B in that regression line is the direction of the relationship. Again, it's going to tell us that sign of whether it's positive or negative. Then we evaluated R squared here at the bottom, which actually measures the strength of the relationship, and that is designated by the proportion of the variance in Y that is explained by X. So again, this first half of the lecture really focused on the idea of correlation, and we kind of finished up with a little bit of regression. Again, this is a higher level concept that you really won't run into much unless you go into a higher level statistics course. But again, if this piqued your interest at all, I'm more than happy to speak with you about it if you would like to discuss it more. So in summary, there are 3 central questions that we can ask ourselves when we are assessing correlation. The first is simply whether a relationship exists or not, and we can see this visually by simply looking at a scatter plot. We also learned, though, with Pearson's R, that we can assess 2 elements, both the strength and the direction of the relationship of a correlation, right? Between two interval ratio level variables. And that we can view on a scatter plot, but also with that R value itself. We can assess the direction of it, whether it's positive or negative. That's going to tell us the associated correlation, if it's a positive correlation or a negative correlation. And the strength of that is going to depend on the range of values as well. So we know that a perfect negative correlation is going to have a value of -1. No correlation is going to be our middle point of our range of 0, and a perfect positive correlation is going to be a value of +1. As a reminder, in our social world, we rarely, if ever, see a perfect positive or negative relationship. And so what we're really doing is just assessing the strength of the relationship in terms of, is it a moderately strong relationship? Is it slightly? And we saw various examples of that throughout today's lecture, right? The relationship between height and shoe size was very strong relative to some of the other ones we saw. And so keep that in mind as you view different types of questions. The closer you get to either end of this distribution, the stronger the relationship you will have. Again, we took a look at Pearson's R as well, the correlation coefficient. And overall, keep in mind that correlation does not equal causation. So even though we've talked about various times how these association measures can give us a lot of information about the relationship between two variables, it can't definitively tell us that one variable is causing an effect on the other. We lastly finished with the estimation of the regression line. Remember that regression is our line of best fit. And the resulting regression formula from that allows us to estimate various elements about our dependent variable. And so we took a regression equation and we were able to predict someone's GPA based on the number of hours they spent studying. And so that's kind of the extra step that regression allows us to do that a simple correlation and viewing that relationship does not. And so if you have any questions about this material, please let me know. This is your final chapter of content before your final quiz. And so I want to make sure that you have a really firm understanding of this before diving into your review materials. And as always, I will see you in the next video.